Hello everybody, welcome to this video looking at the alternating series test. So we've recently seen the integral test and the comparison test for divergence or convergence of integrals, but those were only for integrals that have positive terms. So what happens if the terms are not positive? How do we test convergence and divergence? So we're going to see a few tests. The first one, the alternating series test, is when the pattern varies the pattern of the signs varies in a very particular way. It's first a plus, then a minus, then a plus, then a minus, then a plus, then a minus, or vice versa. So it alternates. After each plus there is a minus, after each minus there is a plus. And it turns out that this creates a lot of cancellations that makes it somehow easier for the series to converge. Okay, so let's see how it works. So as we said, these refer to series of positive terms. What if the signs can change? We're going to study alternating series, which is when the signs alternate between plus and minus. For instance, here we have a series 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on. It starts with a positive, then a negative, then a positive, then a negative, and so on. And if we had to write that in sigma notation, it would be the sum of minus 1 to the n minus 1 times 1 over n. So here the minus 1 to the n minus 1 captures the alternating n sign. For instance, if you plug in n equals 1, you're going to get negative 1 to the 0, which is 1, so it's a plus. If you plug in n equals 2, you'll get negative 1 to the power of 1, which is minus, so you get a minus and so on. But also, I mean, it's the same thing if they start with a negative sign and then they alternate to positive. It doesn't matter whether we start with plus or with minus, as long as they alternate. The clue is, I guess, in the name. For instance, this one, minus a half plus 2/3 minus 3/4, and so on. So here we're starting with a negative instead of starting with the positive that we had before. So here the right way to capture the sign is negative 1 to the power of n, so that when we sub in n equals 1, we get negative 1 to the 1, which is 1. So generally, alternating series are always written as a sum of an, where the terms look like negative 1 to the n minus 1 or negative 1 to the n times some positive part. So there is this alternating part captured by negative 1 to some power, and then there is the positive part bn. Okay, so what is the alternating series test? So suppose we have an alternating series, so it could either start with a plus or with a minus. Here I wrote when it starts with a plus. So it looks like b1 minus b2 plus b3 minus b4, where bn is strictly positive. So it's the sign is alternating, and then bn is just the positive part. And let's suppose it satisfies two conditions on the positive part. So the positive part is decreasing. Bn plus 1 is less than bn for every n. So the positive part is getting smaller and smaller. And the positive part bn is going to 0. Then the conclusion is that the sum of the alternating series converges. So notice here we're gaining a lot from having alternating series, right? If you didn't have alternating sign and you just had bn decreasing and going to 0, then that would not be enough. So here the alternating sign really helps us. But if we have an alternating series, this is a very powerful test, right? We just look at the positive part, we check the positive part is decreasing and goes to 0, then the series converges. Okay, and it's similar if we start with a negative term. So it doesn't matter if it's negative 1 to the n minus 1 or negative 1 to the n or whatever. As long as it's alternating when you write it in terms, you can try to apply this test. Okay, so here's a pretty typical example, maybe a very important example. If we start with the sum of negative 1 to the n minus 1 times 1 over n, or if we write out the terms, that's 1 minus a half plus a third minus a quarter plus a fifth, and so on. So it's an alternating series. So, and the positive part is 1 over n, right? The sign is alternating, positive part is 1 over n. The positive part 1 over n, it's decreasing. It's getting smaller as n gets larger, and it converges to 0 as n goes to infinity. Okay, so we have an alternating series. The positive part 1 over n is decreasing and goes to 0. Hence, by the alternating series test, the original series converges. Okay, so this series has a name. It's called the alternating harmonic series because it's almost the same as the harmonic series, which would be 1 plus a half plus a third plus a quarter plus a fifth and so on, but the signs are alternating. So for obvious reasons, it's called the alternating harmonic series. Okay, so let's just compare. If we look at the original harmonic series, 1 plus a half and so on, this diverges. So this we studied, for instance, it's a p series with p equal 1 less than or equal to 1. Or there was a proof some videos back of why the harmonic series diverges. But if we add the signs in, if we make it alternating, then it converges. So that's quite surprising. This is one important thing to remember, the difference between the harmonic series and the alternating harmonic series. So normally terms going to 0 is not enough. But if the signs are alternating and the positive parts are decreasing and go to 0, that is enough. Okay, but let me say, have caution. So the alternating series test is very powerful, but you still need to check the conditions. It's not true that every alternating series converges. For instance, here's an alternating series, negative 1 to the n, and then the positive part is 3n divided by 4n minus 1. So it's nicely alternating, but it doesn't converge. For instance, if you try to use the divergence test, remember the divergence test, we said, look at what happens to the terms. If the terms don't go to 0, if they don't converge to 0, then the series diverges. So here the terms 3n divided by 4n minus 1, that's going to 3 over 4. And then there is this piece that alternates between plus and minus. So it's sometimes close to 3 over 4, sometimes close to minus 3 over 4. Okay, this is definitely not converging to 0. So the terms don't go to 0, hence the series diverges. So why even though it's an alternating series test, does the alternating series test, sorry, why even though it's an alternating series, does the alternating series test not apply? Well, for instance, if we look at 3n divided by 4n minus 1, it's not convergent to 0. Okay, and we didn't even check it's decreasing, but in particular, it's not convergent to 0. So we cannot apply the alternating series test. So do check the conditions. But don't let me scare you off. If the conditions are valid, if they're satisfied, then this is a very powerful test. For instance, another example, sum of negative 1 to the n, 1 over ln n, 1 over ln2 minus 1 over ln3 plus 1 over ln4. This is another series that if you didn't have the alternating sign, it would diverge, but with the alternating sign, it will converge. So whenever you see an alternating series, it's natural to check the conditions for the alternating series test. It should be your first thing. If you see the positive part doesn't go to 0, then that's a suggestion that it will diverge by the divergence test. Okay, so do check the conditions on that. Okay, why is this true? Just a brief aside. So suppose we have an alternating series with positive part Bn. The positive part is decreasing and goes to 0, as in the alternating series test conditions. Okay, then let's make this funny calculation. Let's look, remember Sn is the sum of the first n terms. So let's look at S2n, which is the sum of the first 2n terms. And if I want to sum the first 2n terms, one thing I could do is I could sum up the first 2n minus 2 terms, and then I could add the 2n minus first term, and then add the 2nth term. And because the terms are either plus bn or negative bn, the 2n minus first term is b2n minus 1, and the 2nth term is negative b2n because of the alternating sign. And then if we look at what's happening, the way it's grouped, b2n minus 1 minus b2n, remember the b's are decreasing in the conditions for the alternating series test. So b2n is going to be less than b2n minus 1. So in the parentheses here, there is something positive. Okay, so the thing we have here, S2n is bigger. If we just throw away the positive thing in the parentheses, it's bigger than S2n minus 2. So what this is saying is that S2n is an increasing sequence. If I sum 2 terms, and then I sum 4 terms, and then I sum 6 terms, if I sum an even amount of terms, that's an increasing sequence. Okay, but here's another funny way of looking at the sum S2n. So we do B1 minus B2 plus B3 minus B4 plus B5. So if you were to expand these brackets, these parentheses, it would be exactly the sum if you were to write it out with the signs coming from the fact that it's an alternating series. But they're grouped in this funny way. So what is happening here? Well, remember that B's are decreasing. So here, B2 minus B3, if B3, we know that B3 is less than B2. So B2 minus B3 is going to be positive. And similarly, B4 minus B5 is going to be positive. So all these terms are positive. So if we want to get an upper bound, if we want to make it bigger, that means we can just drop off these negative terms. So negative of something positive is a negative term. So we can drop all the negative terms. This is going to be less than or equal to B1. So this tells us that S2n is also bounded above. If I sum 2 terms, 4 terms, 6 terms, and so on, that's a sequence that is bounded above. Okay, so it's increasing and bounded above, hence it's convergent to some number. Remember we said that by the monotone sequence theorem, every monotone bounded sequence is convergent. In particular, every increasing sequence that's bounded above is convergent. So we didn't quite show that the partial sums are convergent yet, but we showed at least that the even partial sums, if we sum 2 or 4 or 6 terms, then they are convergent. Okay, but there is an easy way to jump to the 2n plus first. So if we want to add 2n plus 1 terms, we can first add 2n terms and then add the 2n plus first term. And rather than take the limit of S2n plus 1, we can take the limit of the right-hand side instead. We just said that S2n tends to some number S, and then the b's are going to 0 by our conditions in our alternating series test. So this goes to S plus 0, which is S. Okay, so now we've managed to show that both S2n and S2n plus 1 both converge to S. So if we sum 1 plus 3, 1 term, 3 term, 5 terms, 7 terms, or if we sum 2 terms, 4 terms, 6 terms, they're converging to the same number. So putting it together, the partial sums are going to converge to the number S. And partial sums converging means exactly that the series converges. Okay, so if you got lost here, now is the time to come back. But yeah, this is why the alternating series test is true. It follows from the monotone convergence theorem for sequences. Okay, so moving on. So there is one last thing we have to understand, which is the alternating series estimation theorem. So if you remember back to when we did the integral test told us whether a series converges or diverges. It didn't tell us what it converges to. So we said that one way to estimate it is to add up a lot of terms. And then we want to know how large the remainder or the error was. And in that case, there was an error or a remainder estimate involving integrals. We could say the remainder was less than some integral that we could calculate. Okay, here that doesn't make sense because we're not assuming that things come from functions and we're not able to use the integral test because things are not positive. So we need a different way to estimate the remainder. So let's suppose we have a series which is alternating. So an alternating series, and it satisfies the conditions of the alternating series test. So the positive part is decreasing and tends to 0. So this series converges by the alternating series test. And let's suppose that we add n terms to get an estimate for the sum. So that's Sn. And we want to know how good an estimate that is. So that means we want to know how big the error is. We have to look at the difference between the true sum S and the remainder and the partial sum Sn. So as before, this is the same remainder. It's the error if we only add n terms rather than adding all the terms. Okay, then there is a simple estimate for that for alternating series. So that in particular for alternating series, the absolute value of the remainder is less than Bn plus 1. So what does this mean? If I add n terms, then the error is at most Bn plus 1. Bn plus 1 is the positive part of the next term along. So we are saying if we add up n of the terms, how large the error can be, it's at most the positive part of the next term, so of the term that we did not sum. Okay, so let's do an example on that. So this is the idea of estimating remainders is the same, but the estimate we actually get is completely different. One, in the integral test, it depends on using the integral test. Here, it depends on having an alternating series. Okay, so let's, for example, find the sum of find the sum of -1 to the n of n factorial to 3 decimal places. So we see the -1 to the n there on the top, so we see that it's going to be an alternating series. The positive part, which is the part without the alternating sign, is 1 over n factorial. That's decreasing and convergent to 0 because the bottom n factorial is increasing and going to infinity. So we do 1 over, we get decreasing and convergent to 0. Okay, so by the alternating series test, this series converges. The sum of -1 to the n of n factorial converges. Of course, it doesn't tell us what it converges to. So, but we know by the test we just said, the remainder estimate we just said, that if we add n terms, then the remainder is at most Bn plus 1, which is the positive part of the next term long. And now we just have to kind of do trial and error to see to get the remainder small enough. So we want to estimate the sum correct to 3 decimal places. So for sure, we're going to need our errors to be less than 0.001. We don't want the third decimal place to change. And probably we need it quite a bit smaller than that because we don't want any uncertainty due to rounding errors. Okay, so just there's no easy way to say how many terms we need, but just a silly example. If we were to only add 2 terms, then we would have R2. The remainder, if we only add 2 terms, it's less than the next term along, which is B3, or the positive part of the next term along, which is B3. Okay, and that will be 1 over 3 factorial. The positive part is 1 over n factorial. B3 will be 1 over 3 factorial, which is 1 over 6. And that's 0.1666, which is clearly way too big. If you have an error of 0.16666, you can't say anything correct to 3 decimal places. So we keep adding and keep adding more terms. And by trial and error, if we add 6 terms, then the error is at most the 7th term. And it turns out that here the 7th term is less than 0.0002. Okay, you would get nicer numbers in an exam. But here, if we add 6 terms, the error is at most the positive part of the 7th term. That's 0.0002. Okay, we might suspect that that is a small enough error that we are able to nail down the sum correct to 3 decimal places. So what will be the sum? How do we do that? So we are saying we add 6 terms. If you plug in 6 terms and plug it in a calculator or something, S6, it turns out just by doing 1 over 1 factorial, 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial, writing out the terms up to the 6th, gives us S6 is 0.368056. And if we look at what happens if we add 0.0002 or we subtract 0.0002, if we are within distance 0.0002 of 0.368056, then still this 0 could change to a 0, a 1, or a 2, or an 8 or a 9. But still we are going to have 0.368 to correct to 3 decimal places. Okay, so here the sum is 0.368 correct to 3 decimal places. Okay, so just to summarize, we talked about the alternating series test. If it's an alternating series and the positive part is decreasing and tends to 0, then we have a very powerful test that says the series converges. And then there is an estimate for the remainder if we only add n terms for a series which satisfies the alternating series test. The absolute value of the remainder is at most the positive part of the next term along. Okay, thanks.